Hey, Chris, how many times have we seen this diagram presented?
A lot of times, Greg.
A lot of times,
A lot of
man.
times.
It's always presented in a way that seems like everybody should already know everything about it. Have you noticed that, man?
Yeah, I have.
Yeah. You know, and I think this is exactly what motivated this journey we're about to go on together with everybody. We tried to present this recently, didn't we, in class in just 2 hours, and it wasn't enough. That was wild, wasn't it?
Not enough time.
Yeah. Well, you know, I think that today we have enough time, and everybody that's joining us is in for an epic adventure through the real transformer, soup to nuts. Are you ready to get after it for the next few hours, Chris?
I am so ready, Greg.
Yes. All right, let's go ahead and start getting into it then, everybody. We'll have Chris back in just a little bit as we kick off some code. My name is Greg Loughnane, and I'm the founder and CEO of AI Makerspace. That's my man, Chris, also known as the LLM Wizard, the co-founder and CTO. This is an event that we've wanted to put together for quite some time, and we thank you for joining us today or watching after. We're going to try to break down every single piece from concepts to code to calculations in matrices as best we can of the transformer. So let's not dilly-dally any longer, and let's align our aim for the day as we always do at AI Makerspace. By the end of the day today, you will, if you stick with us, grok the transformer architecture and also the mechanism of attention. At a high level, you'll develop some intuition, and you'll also understand nuts and bolts. How is it really being calculated? We're going to build a transformer from scratch. We're going to train the transformer from scratch that we've built. So there's a lot to do today, from the high level overview to understanding attention and how it's calculated, understanding how we put text into a transformer, how it processes that text at inference, how to put each of the pieces together after we code them up separately. And then, of course, we have the whole thing done. We've got to train it. And so let's get to it. The transformer introduction generally goes something like this, which is hilarious because this is not what ChatGPT looks like, and it's not really what any of the large models today look like either. And by the end of the day today, you're going to really understand why. It also isn't this, which so often, you know, people want to throw this up and they want to, again, push this idea that everybody should know about transformers. So let's start with the source material, shall we? Let's start with the paper, Attention is All You Need. And let's read a few key statements here that we can start getting to know. Let's settle in, everybody. The dominant sequence transduction models of the day when this was published were based on complex recurrent or convolutional neural nets. That included an encoder and a decoder. The best performing models in that paradigm connected the encoder and decoder through an attention mechanism. None of this stuff is really brand new here. The transformer, in a fundamentally different way, dispensed with recurrence and convolution and created something based solely on attention. This allowed things to be trained faster with being almost as performant. And they noticed that when they did this, it generalized very well to other tasks. This is the context in which we need to approach the transformer. Yes, we can go down the rabbit hole with recurrence and convolution and all of the things that were happening with attention before attention was all we needed. But that's not where we're going to go today. We're going to focus on what we can learn by studying the transformer from the original paper. At a high level, the transformer in this form that is from the original paper is going to be very good at lots of things. One classic thing that this type of transformer is good at is a translation task. Je suis student. I am a student. Here we go. That's the big idea. If we break this down, though, we can start to see that this is actually an encoder block, and this is actually a decoder block. So we can look at this architecture more like this. As mentioned in the original paragraph, we can put something in to an encoder block. We can connect it to the decoder block through attention, and we can get something out. Let's take a closer look at encoders and decoders. The stacks, again, from the paper, we read. The first thing we have to consider is the encoder. And the encoder is composed, first of all, of a stack of 6 identical encoder layers. All right, we'll come back to that, but keep that in your mind. Each layer has 2 sublayers. A self-attention layer, a multi-headed self-attention layer, and a second simple position-wise fully connected feed-forward neural network. Okay, got it? Stack of 6, 2 sublayers, self-attention, simple feed-forward neural net. All right, what about the decoder stack? Well, the decoder stack, same, n equals 6, but in addition to the 2 sublayers, the decoder inserts a third layer, this self-attention layer at the bottom here, which performs multi-head attention over the output of the encoder stack. So after we get something coming out of the encoder stack, it goes in to this multi-headed attention layer here at the bottom. This self-attention layer in the decoder stack is modified to prevent positions from attending to subsequent positions. This masking, this masked multi-head attention, combined with the fact that the output embeddings are offset by 1 position, masking plus offset, ensures that the prediction for position I can depend only on the known outputs at positions less than I. What are we saying here? We're saying that through offset and masking, we're doing next word prediction based only on previous words. We're masking the word that we want to predict next, and we're only looking at words that came before in the sequence. All right, classic, right? Classic thing to do. This is what all the GPT, this is the next word prediction machine. This is the decoder stack. All right, so if we look at both encoder and decoder stacks, we see something interesting happening here. We see, and this should say encoder and decoder stacks. We see there's also a residual connection around each of the 2 sublayers in both of these stacks, followed by a layer normalization. In other words, there's a layer norm of what we're pulling from before the sublayer and what we're calculating in the sublayer. How does this look? Well, let's go back to the diagram here. We're talking about the layer norms, this add and norm, and we're talking about these residual connections. Okay, we're pulling X, and then we're also moving through. If we sort of combine this, take this example right here, we're calculating the layer norm of X plus what's calculated within the attention sublayer. Whereas here, we're pulling X, we're doing the layer norm of X plus what's calculated in the feed-forward neural network layer. All right. Ultimately, we get some outputs. The output is of some known size, and we can compute the probability of what's going to be the most probable next word. That's the one we're going to predict. All right. So there's stacks of encoders and decoders. This is one encoder. This is one decoder. But there's many encoders and decoders, 6 of them in the original paper. In each encoder, there's 2 sublayers. There's a self-attention layer and a feed-forward neural network layer. There's a residual connection around each, followed by a layer normalization. The decoder is the same. However, because of the masked self-attention layer at the bottom and the offset of the outputs being shifted to the right, we're actually producing the effect of predicting the next word. So what we haven't covered yet is we haven't covered the input, output, embeddings in detail. We haven't covered positional encoding. We haven't covered the output, which is pretty classic output thing in machine learning. But we'll come back to these. All right. For now, let's zoom out a bit to put some of these tactical details in context. What the encoder is actually doing is you might say it's focusing on understanding the input. This is true for encoders generally. And this is why when we use an encoder-only architecture, we're going to focus on tasks that require this understanding. Or if we use an encoder-decoder style architecture, we would also want to pick a task that it's important to understand the input, like a translation task. The decoder uses understanding from the encoder in this stack. That's where it comes in with the multi-headed attention, the encoder-decoder attention, and it generates one word at a time, as we talked about, the mask, the output shifting. Now, if we look at an encoder-decoder style, that is called a BART style model, because there's a model called BART that they produced a paper about, and it's good at generative tasks that also require an input, like the translation task we saw or summarization. Now, what does BART stand for? It stands for bidirectional autoregressive transformer. Autoregressive simply means predicting future values based on past values, next word prediction. And bidirectionality is talking about understanding the sequence from both the left and the right. So it's an encoder-decoder or sequence-to-sequence model. It's bidirectional like a BERT-style model, and it's also autoregressive like a GPT-style model. So a BART-like model uses both encoder and decoder. Great. If we want to look at encoder-only models, we would be looking at BERT-style models. This is focused on understanding of the input, fundamentally. And so when we look at something like sentiment analysis, this is a great example, because we really want to understand what was said so that we can try to predict something, right? In that case, it's a binary or multi-class classification, positive, negative, neutral, or positive, negative. And there are many such examples that you'll find that BERT-style models, or smaller BERT-style models like Distill-BERT or Distill-Roberta, you can find these models in lots of different use cases. And they're still, used today if you need to pick up something smaller, but still very performant at tasks like these. Now, what does BERT stand for? BERT stands for bidirectional encoder representations from transformers. Makes sense. All right. And the BERT style model looks like just this piece. All right. Now, a decoder only style model, that's a GPT style model, just like OpenAI's GPT series, just like Llama 2, just like all of the models that are coming out all the time. Falcon 180B, Yi from the other day, 1.AI's Yi, lots and lots of models coming out, Mosaic GPT, lots of models all the time. Okay. These are good at generative tasks, as we're comfortable with. And GPT simply stands for generative pre-trained transformer. Simple enough. If we look at something like GPT-2, we'll see that it has 12 decoder blocks versus, as we saw in the original paper, we're looking at 6 and 6 encoder and decoder blocks on the transformer. Decoder only looks like this, which brings us to attention. This is sort of one of the key aspects that we need to understand. I mean, attention is all you need, right? So we're going to kind of start with attention today, even though you'll find attention sort of buried within the transformer. We're going to start there and then put together all the other pieces because it's really essential to understand what's going on here. We're going to talk about how it's calculated, and then we're going to talk about how to think about it. From the paper, an attention function can be described as mapping a query and set of key value pairs to an output, where the query, keys, and values and output are all vectors. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. A lot going on here. This is why so many people don't spend the time to really break this down. But this is exactly what we're doing today. So let's check this out. This is from Jay Alamar's illustrated transformer. And let's read this again with this in mind. An attention function can be described as mapping a set of key value pairs, a query and a set of key value pairs to an output, where the query, keys, and values and output are all a vector. The output is computed as a weighted sum of the values, So the weight here is this softmax calculation. And the softmax times the value is how we're getting this output. The softmax is the weight assigned to each value, and it is computed by this compatibility function of the query with the key. So we compute this score, we divide by 8. This is the dimension of the key here. This is the square root of the dimension. And we get this softmax, square root of the dimension of, I'm not sure if this is key, but it's square root of this dimension. Let's look at the actual equation for this from the paper. The attention of query, keys, and values is the softmax of query times key transpose divided by the dimension times the value. What we're seeing here is simply the calculation of scaled dot product attention, bottom up, for a single vector. Okay, a single vector in this case, you'll notice a single embedding vector refers to a single word, thinking machines in this case. But generally, we're going to have more than one word. So what we actually end up doing is, in practice, what we want to do is we want to compute the attention function on a set of queries simultaneously, packed together into a matrix Q. The way that we pack these things together is we go ahead and take thinking and machines and we stack them. And we stack them, and we stack also the queries, keys, and values, and we multiply these stacks together. It looks something like this. So we're sort of expanding this idea of a single vector representing a single word, getting some final output, and we're expanding it to multiple words. So we have matrix versions of query keys and values. Once we have matrix versions of query keys and values, then we can calculate matrix outputs. So fundamentally, attention here is this Z output. And attention, if we sort of think about how all these diagrams fit together, scale dot product attention goes into multi-headed scaled dot product attention. And that multi-headed attention is baked into each of these attention layers within encoder and decoder blocks. Now, note that you should also be paying attention to the fact that this is a multi-headed attention. All right. So we can calculate attention. We can calculate attention for many words. But now we want to calculate multi-headed attention for many words. So let's think about how we do this. Well, if we have our input embedding, then we might want to calculate our query keys and values matrix for each attention head. As we calculate it for each attention head, then we run into this situation where we've got our attention calculated outputs for each head within a single attention layer. However, in order to pass this thing both through the residual X and into the feed forward or next attention layer, we need to put all of these attention heads back together again. And what we want to do is we want to essentially take each of these attention heads, turn it back into something that looks like it came from one, and send this forward. Send this through the residual, send this to the feed forward network, send this to the encoder-decoder attention. Why are we doing this? Well, we're doing this because multi-head attention from the paper allows the model to jointly attend to information from different representation subspaces at different positions. This sounds complicated because it kind of is. It's pretty epic. Different representation subspaces. Okay, that sounds cool. Is it as cool as it sounds? I mean, I think so. We'll talk about that shortly. But what you need to know for right now, while this is still hanging in your brain that we just built up, is we're talking about this output from the attention ready to go into what comes next. All right. So we want to figure out what's going in, what's coming out of attention. And we're going to start messing with a diagram that looks like this, that we created, Chris created himself. And we're going to start walking through it, starting with coding multi-headed attention. So with that, I'll hand it back off to Chris to show us exactly how this is done.
What's up? Yes, so multi-head attention. The idea is exactly as Greg stated. So the idea here is we are trying to, we're trying to create a system by which we can attend to many different things in which we can have each of our heads be a quote unquote expert on different parts of the sequence. And so that's going to be, and I'll share the link, sorry, so you guys have it in the chat. But the idea here is that, we just need to code this up. And it's not very difficult to code it up. The first thing that we want to do is actually separate this out. I'll zoom in a little bit here, so hopefully you can see that a little bit better. But the idea here is that, we have some number of, that describes the dimension of the information flowing into our attention block, and that's going to be this 512. And then we have a number of heads that we desire, which is going to be this the default of 8. The idea is we just need to split each of these into a different chunk, as it were. So the input sequence comes in, and we care to split that into 8 even chunks, and then let each head attend to each part of that sequence. Exactly as Sushima said in the chat here, main intuition is that each head should understand different information about your actual data. And so each head, quote unquote, becomes an expert at a different part of the sequence relationship. The way we think about this or talk about it is the same way that you kind of conceptualize the idea of embedding dimensions, where each dimension is going to correspond to some abstract concept. The same way each head in your transformer is going to attend to different abstract concepts, right? So like in very abstracted, crude terms, you'd have a head that cares about temporal relationships, or that cares about, grammatical relationships. Again, it's not going to boil down that cleanly, but that's the intuition. Is more heads better than one kind of thing. Let each focus on its own thing. But you'll notice in the code, it's very straightforward, right? We have this this input where we have our actual number of dimensions that we're going to deal with, the number of heads we desire. These numbers must cleanly divide. So we have a check here. The check is just saying that the dimension of the model is cleanly divisible by the number of heads that you have. So we're going to use Python's modulus operator to do that. The remainder should be 0, so we just assert that it's equal to 0. And then we have this dk. This is going to be the dimension of each of those individual heads. And then we're going to do our classic, forward layers or linear layers for each of our weights for a key, query, and value. Now, we're also going to, and this is the output layer, which is just, again, a linear layer. We also have this first time we're going to kind of talk about dropout regularization. These models tend to super overfit. We're going to see a ton of different methods used throughout our, our journey today that are simply meant to, ensure that training is stable, right? We're going to train these things on a huge volume of data with a huge number of weights. So you're going to see a lot of different things to ensure that our training is stable and to promote a well-regulated network. And so this is the first time we see that in the code, which is just some dropout. So this is the actual multi-head attention class, but we need to define some methods. So let's do that here. The first one we care about is this scaled dot product attention. Now, it looks kind of like maybe confusing, but we'll go through in the code and it's super straightforward. The idea is that we have our queries and keys and then our value. And basically what we're going to do is we're going to use this scaled dot product in order to determine some amount of information from our queries and keys. And then we're going to multiply that again together with our values. So in code, right, it's pretty straightforward. Now, keep in mind that this is for each head. We have our query, key, value. We're going to accept our attention mask in case we have a attention mask. This dk, or this dimension, is going to be what we derived above, which is just the dimensionality of the model divided by the number of heads that we have. Then, again, we have this dropout, which is by default going to be none, just regularization technique. In order to actually get our attention scores, I'll just scroll up so you can see both pieces of information here at the same time, right? We're going to do this query mat mold with the transpose of our key. Notice here, that's exactly this box, right? This is all this is doing. Then we're going to scale that, and we're going to scale it by that relationship between the two, between the dimension of the model and the number of heads that we have. And when you think about it, it kind of makes sense, right? We know that there's going to be 8 heads, so we want to scale the contribution of each head so that it's proportional to the actual number of dimensions of our input sequence that's attending to. We are going to grab a softmax. If we care about the mask, we can apply it here. But then we're going to do our softmax to grab just a bunch of scores. And then we're going to do this matrix multiplication again with our attention scores and our value. And what that's going to do is it's going to get us back to the dimensions that we desire, right, for each head. And it's going to apply those attention scores across all of our values. So we're going to have a resultant value that's going to take into consideration the attention scores we calculated based on our queries and our keys. And that's it for the scale dot product attention, right? So just the code, it's fairly straightforward, right? We do this matrix multiplication, we scale it by a proportional value based on the number of input dimensions we have and the number of heads we're using. We're going to softmax those attention scores, and then we're going to apply those attention scores across all of our values with that matrix multiplication that you see here. We're also going to return our attention scores just for, in case we want to use them or we can leverage them later. You don't necessarily need to do this step, but it's still, it's something you can do, so why not? So this is great. So now we have the idea, right? We have these layers for each of our query keys and values. We have our output layer. We have the ability to calculate this, scale dot product attention with this attention method. And now we just need to tack it all together. So the first thing that we're going to do is we're going to initiate our WQ, WK, WV layers with the value from the feed forward step, right? So we're going to pass information into these and populate each of these values. Then we're going to construct these views. Basically, all we're doing is we're chopping these query key and value, weights into the correct size chunks. Then we're going to use that to calculate our attention scores with our scale dot product attention method that we set above. And then we're going to rework them back into the correct shape. We're going to ensure that we have the exact same shape that we had coming in. And then we're going to pass that through our feed forward or linear output layer. And that is it. In one big block, right? This is what we have. This is the whole brain, right, behind the operation in terms of that multi-head attention. It's very straightforward. All we need to do is convert our data into the appropriate type, which we're going to do here. Chunk it into the appropriate sized chunks with these 3 lines. Calculate our attention scores, which we're going to get again from the process that we outlined. And then we're going to pass them through that final output linear layer. And this is self-attention, right? This is scale dot product attention. This is what we're going to use to power our encoder and decoder blocks. This is all we need to do to really get started. And the code is, this is not a lot of lines of code in terms of like how powerful this system is. And that's it, And yep, that's a great thing to say, Peter. You don't calculate QKV. You are learning QKV as you progress through your training. We use them to calculate attention scores, and that is that. And with that, we'll pop her back to Greg.
Yeah, all right. So attention, check. It's all we need. And we saw that attention, again, straight from the paper here, we had encoder-decoder attention. This is the attention that allows every position in the decoder to attend over all positions in the input sequence. And then, of course, the encoder has a self-attention layer and the decoder has a self-attention layer. Of course, we're preventing that leftward information flow into the decoder to preserve that predicting the future from the past, that autoregressive property. Okay, let's zoom out again. We were having a bit of a discussion, I think, in the chat, which is really cool, talking about self-attention. It's important to kind of understand how it's operating, and that's kind of what we just talked about. It goes through the encoder, and then it does the decoding. This is sort of a great little image here. If we could just sort of walk through it as it starts over, I think it's going to be useful before we talk at a higher level. So, the transformer starts by generating embeddings for each word. So those are the unfilled circles. Using self-attention, it takes into account info from all of the other words. That's what it's doing here. This step is repeated multiple times. And the decoder is operating similarly. The decoder is at the bottom here, but generates one word at a time from left to right, while paying attention not only to previously generated words, but also to the final representation generated by the encoder. Okay, so this is kind of at a high level what's going on. Let's go a higher level. Let's look at an example. Self-attention is really just looking at each token and deciding which other tokens are most important to understanding the meaning. So if we think these two examples, I have no interest in politics, or the bank's interest rate rises. We're talking about different interest. What should we be attending to figure that out? Well, in the first case of I'm not interested, maybe it's no and in are the most attended to words. And in the second case of bank interest, perhaps it's rate and bank, right? This is the big idea. Remember, the transformer is taking an input, running it through encoder-decoder stack, and getting an output. And there are many layers of encoders within the stack, more than are visualized in that initial transformer diagram. There's many layers and many stacks for the same reason that two heads are better than one. And we're sort of making this attention within the encoder and the decoder and the one that connects the two kind of more and more useful and powerful to sort of figure out the meaning of what we put in, and this helps us get the right thing out. So, self-attention helps the encoder look at other words in the input sentence as it looks at a specific word, and that encoder-decoder attention, which is still self-attention, is still that scaled dot product attention, is helping the decoder focus on relevant parts of the input sentence, as we saw in the visualization. Remember that multi-head attention is important. And as we saw in the paper, and as you guys kind of talked about in the chat, it's kind of like thinking brains in a vat a little bit. We We want to sort of have each head figuring out some other part of the universe of the world. We want each head to be focusing and attending to some other aspect of, let's say, the entire space of understanding we need, depending on the application. In the largest language models, we really want them to understand the world generally. And so you might imagine these heads are sort of, the departments at a university, or they're sort of looking at specific types of problems. You might imagine that they're breaking things up in ways that are natural to be broken up in the world. At least if we find out eventually that's exactly what they're doing, that's going to really seem to align. And we have many blocks. We have many heads. This is from the GPT paper, the original GPT paper. And you'll notice here it's a little more specific. We've got 12 blocks, and then we've got many attention heads within each multi-headed attention. It's interesting to note here, we see that residual is fed ahead before the layer norm. It makes it a little bit more clear here in this particular GPT paper. Okay, so let's return, shall we, to what we haven't covered yet. The input-output embeddings here, input embedding, output embedding here on the diagram, and then the output that we actually already saw this output within attention, right? We already saw the linear to softmax in the attention itself, in the attention block itself. So these are pretty classic ideas, but let's sort of think about embeddings and positional encoding real quick. In order to create embeddings, we got to tokenize words first. Tokenization, simple idea, chopping up words. In order to create embeddings, we need to create a dense vector representation of those words or sentences or sequences or tokens, basically, in this case for us. And then we want to put the words in the right sequence relative to one another. In previous sequence-to-sequence models, convolution and recurrence took care of that for us. In transformers, they do not, because attention is all you need. Attention with some positional encoding information. So tokenization, let's talk about it just real briefly. It's real simple. You chop up words. Here's an example. Chopping up words into pieces. Friends, Romans, countrymen, lend me your ears. Now, we're getting rid of commas a lot of times. We're getting rid of stuff that doesn't seem to help us to decipher meaning. We're getting rid of a lot of stuff, classic NLP status. And so we're left with kind of subwords. And there's right and wrong ways to do this, and you can talk about tokenization strategies. What's the right way to tokenize aren't, for instance, right? It's not exactly are not. It's probably closer, if we can get close to are not, probably feels a little bit better. But, is there a right or wrong way? You can quibble over it, but we can get pretty good results with pretty standardized tokenization strategies these days. So tokenization into subwords is well studied. It's we've got some great tools that we can pick up off the shelf. Same with embeddings. Although more and more specialized language does deserve to have some attention paid to embeddings, but for the most part, when we're thinking about embeddings in this sort of from scratch transformer context, we can think about them very simply. We can think about them at the word level. So write has a dense vector embedding, A has a dense vector embedding, and so on. And of course, embeddings are simply turning words into numbers. That's all they are. So we can map them into a space, right? We've shown this before elsewhere, but this is a great little quiz. Where does Apple go in the space that we've charted here, right? Throw it in the chat if you know where Apple goes. It goes by bananas and strawberries and grapes, right? That's where Apple goes. And that's super basic. But then if we start to add a few more interesting specific dimensions and look at specific things, we can start to realize how complexity grows. Puppy is to dog as calf is to cow. So actually cow would go C. So we're looking at maybe age, maybe size, but where does a transformer fit in on this chart? Where does Chris fit in on this chart? Where, does vector math fit in on this chart? These are very disparate concepts, and we need more dimensions by which to measure things. This is the idea of many dimensions of vector space need to be represented. This is an example of a 4096 dimensional embedding space that we're looking at. And classically, we can look at embeddings representing specific words being, added and subtracted and being played with in embedding space. This is, again, very, very well studied. And we've got some pretty solid ways to do dense vector representations. But if you understand that sort of at the token level, the sub-word level, we're creating these dense vector representations, that's what you need to know for transformers. But just because we have the dense vector representation doesn't mean we know where the sub-word, where the token is in the sentence. And that's where positional encoding comes in. Note that positional encoding is not the same as encoder, right? And so you can sort of visualize what's happening here. We're sort of adding a number to each of these. You can sort of envision it here as well, where we sort of have our input word. We have our embedding that represents that sub-word. Then we add some positional encoding to it. And that positional encoding is simply giving us that order representation. The positional encoding sort of details aren't crazy important to understand in the general case. This is sort of a very simple example where we're looking at, how we might add positional information to a simple translation example. The numbers will depend on the sequence and the way we want to do this encoding. But, as long as you're kind of representing the information that you need to represent, you're giving it the order of words somehow. That's really what we're looking for when we head into the transformer. And, that's really the big idea of getting a sentence into encoded embedding vectors that we can then feed in. And, feeding those in is sort of the next piece that we need to look at. Because as we sort of recall our transformer, we know now this is not ChatGPT. This is rather a BART-style transformer, encoder-decoder stack, where we take our input, we create an embedding, we encode that thing, we push it through, code it with positional information, and then what's happening is we're sort of flowing through the system and we output a word. And this output embedding piece is sort of keeping track of words that we output. And I'll show an animation of this in a little bit, but we're sort of flowing through the system. We're outputting a word, and then the output embedding is actually acting as an input to the decoder stack. And in a GPT style model only, of course, we don't have any of this. And we're simply using inputs to the decoder stack with this masked multi-headed attention. And so, we're sort of seeing this prediction of the next word input required that's required for prediction of the next word input coming in to the masked multi-headed attention. So, our image of the transformer looks very similarly. You might note again that a lot of times it's drawn so that the residual is going straight into add norm rather than into the space between add norm and masked multi-headed attention. But when it comes to coding it up, we want to note that we are sort of passing X, and then X is being combined with the layer norm. And that positional encoding piece is what we're going to cover here. Again, it's just imparting information without recurrence or convolution. And so before we go into add norm, feed forward, and closing out the stack here, Chris is going to show us how to set up embeddings and positional encoding. And with that, over to you, Wiz, to show him how to start with the front end of this thing.
Heck yeah. Okay, so we're going to start with our embeddings. And the idea is fairly straightforward. Again, the concepts and the math and the theory behind the transformer architecture is incredible, very dense. Thanks so much, Greg, for walking us through it. The code, though, the code is mostly handled by the library we're going to use today, which is PyTorch. So how do we set up our embeddings? Well, very simply, we set up an embeddings layer that's initialized with our vocabulary size and the dimensionality that we desire to flow through our model. So you can see here we have our D model. This is the dimension of the embedding vector we're going to use as we flow information through our network, and then our vocab size. That's just how many different tokens that we have in our vocabulary. We're going to set those things up, and then we're going to initialize our embedding layer with those with that information. And this is going to let us be able to get embeddings for each of the tokens in our vocabulary that have this desired D model or dimensionality of the model size. The only quote unquote special thing that we're doing here is we're actually going to scale our embeddings by the square root of our model's dimension. This is something that they did in the paper. It has not been kind of pointed to as an incredibly important step, but also it's not been pointed to as a unimportant step. So just kind of boilerplate that follows us along, easy enough to implement. And that is it. This is our embeddings. This is basically how we get it. Every token we see, we are going to return a learned embedding for that token. We do learn these embeddings as we're training our model. So it is important to understand that these are not just some random embeddings. They're actually learned throughout the training process, though they do, of course, start as random. We're gonna learn them as we progress through our training. So that's great. We have our embeddings. Now all we have to do is add positional information to each of those newly embedded tokens, right? So the idea is we're going to have this big stack of tokens that are all embedded, right? So when we look at an input sequence, we're going to get say we have an input sequence, it's 6 tokens. We're going to get 6 elements, which are each going to have our embeddings in them. And what are we going to do? Well, we're going to use math to impart positional information. Now, we're using the kind of standard positional encoding technique that was used in the Attention is All You Need paper. There are many different ways that you could impart this information. Many different ways have been tried, and this is a prime place to tinker with how this information is used. But we're going to keep things simple and stick to the paper. And the idea is that we're going to essentially create a method to add information to the big list of tokens that we have that are related to its position, right? So how we're going to do this is just through some PyTorch. So we're going to have again, you're going to see this D model a lot. That's the dimension of our model. This is kind of the way information flows through our internal model between our different layers. We have our sequence length. Now, this sequence length is the number of tokens that we might have, right? So this is kind of, synonymous with your context window. This is the idea that, there is some length that you're trying to achieve that we're going to hold consistent throughout our training. And then, of course, we have some dropout. Got to have some dropout. So we're just going to set up this 0 array, which is going to be this, by sequence length by the dimension of the model, which makes sense, right? We know that we're going to have a number of tokens equal to the sequence length, and then each of those is going to be embedded, and so it's going to have dimensionality equal to the embedding dimension, which we've already set up above as dmodel. Then we are going to kind of like create just a big old long line of them. We're going to use some math here. You'll notice that we have this exponent with this minus log of 10,000. And this is scaled by the dimensionality of our model. This is straight up just from attention is all you need. So if we look at the attention is all you need, paper, and we look at, I'm just going to pull this up on the other screen so we can look at it together. But the idea is we just have this formula here that we need to apply, and that's it. And you'll see that we have kind of our evens and our odds. That's all. So we go back to this code. All of this is just getting us that information, right? So we're going to apply to our, even embeddings, these, the sign of this value that we were calculating above, and then again, but for cosine. And that's all we're doing, right? So the idea is we're injecting this sequence information into our into each of our embeddings based on the position that it's in. At the end of the day, we will return this to the format that we require, and that's it. When we actually go through this process, you'll notice that we have this X. This X is our base embedding collection. We're going to just add the positional embeddings information to X, and that's it. Then we'll do some dropout for regularization. But that's all we're doing, right? We have a big collection of information that has no information at all within it about its position, and then we inject that information through this formula in order to let our model understand where different information is, or where different tokens are relative to each other, without actually needing to have recurrence or convolutions. So we're basically just giving it like a value that indicates its position in the sequence, and that lets it understand where its position is relative to other tokens in that sequence as well. And that's really it. All we do is we get those original embeddings, and then we inject all of that positional information into each of them, and then we carry on with the rest of our diagram. So with that, we will chuck it back to Greg.
Yep. Awesome. Okay. So now we've got our embeddings, our positional encoding, and attention done. So we've got embeddings, positional encoding, attention done. Now we move on to this add in norm layer. And the sort of 10,000 foot idea here is makes training the model a bit easier, and it allows us to generalize a bit better. When we think about layer normalization, this is again a classic thing to do in deep learning. And so this is not sort of anything really new. What's kind of interesting here, and to me, what the most interesting thing is if we go back to this idea of these residual connections and the layer normalization, this sort of adding in of the previous prior to attention X, and then adding it to a sublayer in this case, attention, in this case, the feed-forward network, that takes X and pushes it through. It sort of adds this kind of beautiful nonlinearity to the system. And sort of the idea, as far as I understand it, is that we're trying to make sure that anytime we calculate attention, that it's actually different from block to block. Like, why would we have 12 blocks if they were all going to calculate the same thing? And so when we sort of introduce this sort of residual into this layer norm step, as far as I understand it, then, you know, we're sort of taking care of that that idea. And, you know, I'm sure Chris will comment on this as well when we see him in just a second. This leads us into the feed forward piece of this, where we're sort of just throwing a classic old neural net in, and it's not real complicated. In fact, if I show you the image, you're gonna be like, oh yeah, I know what that is. It's just one of these guys, right? We're just, you go in, it keeps going. And so this feed forward network, it has 2 linear transformations with a ReLU activation. You know, we're starting to sort of get back down into the very core basics of deep learning and the simplest possible neural net here. And, you know, this is pretty easy to implement. And so we're kind of going ahead and pushing these through the feed forward network before we approach the very next block of the decoder or encoder stack. So as I pass it off to Chris to talk add and layer norm, residual connection, and feed forward neural net, you know, let's I'd love to hear his 2 cents on how he thinks about these things conceptually and in code. So Wiz, back to you, man.
Heck yeah. So let's take a second to look at the diagram. You know, it is the meme, you know, the whole diagram, but also it's got some important information. So let's look at the what we've done so far, right? We've got our embeddings. We've injected positional information into those embeddings. And now we're going to start looking at what's happening in the actual network. Now, one of the things that we want to be really wary of when we're training, again, so many of these features are in the model for training stability, right? And there's been some good papers recently about like, well, actually, if you're training these networks on smaller data sets, you don't really need this stability stuff. And so some people have been removing the residuals and all this other crazy stuff. But for like these really big trains, GPTs, you know, your 6, 10, 30 billion parameter models, your training stability is important. And one of the issues we can run into, especially when we're talking about these attention calculations, is you know, the worrying about vanishing gradient. And the way we kind of cheat around that is by using these residual connections. So those residual connections are just going to add the output back. So we're just going to carry the information forward from before it goes through that attention mechanism, and then we're going to connect it back into the same stream, right? So Harpreet used a good term, residual stream. Normalization, on the other hand, is normalization. It's your classic normalization, right? We use it to normalize. There is a couple caveats with normalization, which is this idea of like, you know, those kinds of layers tend to move towards, they tend to, in fact, very small values. And so, again, this is where these kinds of residuals can help us. And this is where the idea of, you know, precision can enter the conversation. So let's look at how we're going to do this in code. For our first step, the idea is we're going to have this values that we use for our layer normalization. we're going to set a very small epsilon. Like I said, the normalization values tend to be very, very, very small. And so we have the potential for a divide by zero error. We use this tiny little value epsilon in order to avoid that. And then we have our multiplicative and additive information from our gamma and our beta. This is all. We can read more about this here, which we'll just do. But the idea is we have these, you have this ability in these two parameters that are going to help us to ensure that we are dealing with normalized data. As you can see here, we're going to care a lot about our mean and our standard deviation. And then we're going to modify our mean multiplicatively with our gamma. And then the same is true of our standard deviation, but we'll do additive correction with beta. And that's it. A lot of Greek letters here, but the idea is pretty straightforward. This is just normalization. We're not doing anything fancy. It's the same that you'd see everywhere. We're dealing with the mean. We're dealing with that standard deviation. Even if the standard deviation is very small, it doesn't matter because we're going to add that epsilon back in, and then we're going to use our additive scalar to ensure that we're coming up with a good, good value at the end of the day. You might notice that we have this parameter thing here, right? So these gamma and beta are both parameters. This is because they are learned. So they are actually learned through training, right? We figure out what the best gamma and beta are for our model. And that's it for normalization. It's important. We have to do it. It helps with training stability. But these values can tend to be quite small. Because they can tend to be quite small, we actually care quite a bit about the precision that they're left in. So when we're doing things like k-bit training, when we're doing things like 4-bit or 16-bit training, we actually tend to leave these kind of layer normalization parameters in their full precision representation, since they're going to be describing sometimes incredibly small values. And this is our layer norm, or our residual, sorry. All it is we plug it back in. This is it. All we have to do is actually, take our input. We're going to pass it through this dropout. Again, we don't want to overfit. Tons of regularization is going to happen here. And then through our layer norm, which we constructed above. And that's all we're doing. Again, residuals help us avoid vanishing gradient. They are useful for retaining information between the attention layers. We don't want to kind of zero information out. It's not necessary. It's not helpful. And so the residual connection helps us to do that. All we're doing is we're looping that information around. It's nothing more than that. It's just like a little bypass for the data. So I see Harpreet's typed some residuals carried from the input embeddings to the logits form the residual stream. This is how the model remembers things, moves information between layers, stores information, attention. But yeah, absolutely. So the idea is basically, we need to keep this through line of information, and our residual connections help ensure that we keep that. Without the residual, we would risk that information dropping off entirely, right? Or losing that information if that gradient vanishes, and that's not going to let us learn, right? We're in fact going to hit a wall, and so the residuals help to do that. The actual information that's being modified is quite small a lot of the time, right? We're dealing with very potentially small values, and a residual is important to ensure that we're not losing information between layers. We want to gain information for sure, but we really don't want to just lose everything we know, right? And finally, we have the feed-forward network. So basically, this added norm part, all it's doing is it's wrapping this attention mechanism, right? It's saying, okay, we're going to get our attention, that's great, but we have to do some normalization, and we have to do this residual connection so that we can ensure our information is well normalized, but also our information doesn't just disappear on us. Then it comes to the feed-forward network. Now, you'll notice the feed-forward network has the same added norm pattern. So we're going to do the same thing that we did with our attention mechanism to our feed-forward network. And our feed-forward network is basically, it's going to do two really important things for us. Number one, it's going to allow us to understand some nonlinear relationships that might appear in our data. And number two, it's going to move our information back into the expected format for the next layer, right? It's really critical to have this feed-forward network, because without it, like Greg said, we would never kind of move around. We could just calculate attention scores over and over and over again, just get a bunch of averages and kind of not learn anything, right? This feed-forward network is incredibly important. It does those two functions very well, understanding nonlinear relationships, thanks to things like ReLU and JLU and everything like that, and whichever ALU we're on now. And then, of course, it lets us move that information back into an expected format, right? We need to have the next layer get information in a format that it can use usefully. All it is, though, is just a little linear layers, and that's it. You'll notice, however, that our linear layers actually have a separate dimension to the rest of our model. So because we want to be able to capture a lot of information and understand these potentially complex nonlinear relationships, we're going to actually blow up our, we're gonna blow up the dimensions in our linear layers and then drop them back down right away. So you can see this is outlined here. We have our input layer, which is going to be the dimension of the model. The output is going to be the dimension of the feed-forward network. Notice that the dimension of the feed-forward network is huge, right? 2048 compared to the 512 that we've been talking about for our D model. There's going to be a dropout layer because we need to do a dropout, and then we're going to go right back to that large, representation, and we're going to squidge it right back down to 512. Easy peasy. The way this looks in the code is that we have our actual forward method. This is X. This is our input. We're going to first pass X through our first layer, which is going to blow it up to that 2048 representation. Then we're going to do some dropout on that. Always with the dropout. These things overfit like you wouldn't believe. And then we're going to squidge it right back down into that linear layer using the second linear layer. That's all we're doing. The way I like to conceptualize this kind of whole part of the block here, this feed forward part, is like if you imagine, right, the attention scores and the attention heads are taking a look at, say, like an object, right? So if we just imagine this whole process is like trying to figure out what an orange does, right? What's up with an orange, right? We can see by looking at it from the front, it's definitely an orange color, right? We can see it's probably round, it's circular in some way. We get a bunch of information. Now, if we go to the next step and we look at that orange again from the same position, we're not really going to learn anything, to be honest with you. We won't really gain new information, right? So we have to adjust our view, right? Adjust our viewpoint. And perhaps if we adjust our viewpoint, we might notice hidden, behind the orange was a bite taken out of the orange that we never could have seen if we didn't adjust our viewpoint and adjust the way we were looking at this information. And that's how I like to think of the feed-forward network. It kind of lets us look at this sequence from a new perspective, and that's going to let the next set of attention heads understand new, novel things about the sequence that the previous heads weren't perhaps able to see. And so this is the idea. We're going to let these attention heads learn, shift our focus, let that next set learn. And in that sense, you can kind of think of these models as stacks of mini models, right? The idea is we're just looking at it from a different perspective. And that combination of information is going to allow us to build a very rich understanding of these input sequences. But that's all we need to do for the add and norm, the feed forward, and then the additional add and norm block. So we have, up to this point, filled out quite a lot of our chart, right? We filled out, these input embeddings, a positional encoding, multi-head attention, add a norm, and feed forward. I mean, we're rocking along here. So with that, I'll pass it back to Greg.
Yeah, thanks, Chris. And thanks for clarifying that point, that it's not the residual that carries through that different perspective. It's the feed forward network. You know, I love learning things in real time from the whiz with all of you guys. So very cool to make sure that we're clear on that point. And interesting to know how many things are built into the transformer just for training stability, which we'll be getting to in just a second. Linear projection is sort of this last piece we need to kind of decide, hey, which word is next, right? And when we get an output from the decoder stack, you know, we're seeing this sort of linear to softmax thing over and over again. This is a great visualization again from Jay Alomar here. And we're essentially finding all of the probabilities where we're getting the index of the cell with the highest value, the most probable next word. And then we sort of look up this vocabulary word associated with the index. In this case, 5 corresponds to AM. So, you know, we're really sort of just in the end deciding, hey, which word is this? And we're getting the number right at the end that corresponds back to the word. So just as we started in the beginning, words to numbers, get the embeddings, then we've got this decoder stack output that's allowing us to go back from this representation into, you know, we did all of these calculations. We did all of these crazy things to sort of, you know, look at the orange and then look at the dude behind the orange. And all of this stuff was in numbers space. And we're finally coming back and we're saying, all right, now what's next? And it's pretty incredible that, you know, honestly, this works. So I think, you know, a great example here, this is not an encoder-decoder architecture. This is a GPT style example, but this was recently put out by Cohere. And, you know, write a story input, right? We go tokenize the words, we create embeddings, we add positional encodings, we go to the attention layer, the masked self-attention layer. We're going into the feed forward network. We have a series of blocks that go attention, feed forward, attention, feed forward. And now, as we talked about, the feed forward is allowing us to make sure that the next attention layer is going to pay attention to something different. And then we combine all of this together through this linear projection and softmax. And, you know, of course, we need to start it off with once upon a time, right? And then before we see Chris combine this all together again, I really like this example. You know, we can kind of watch this. We see the decoding time step. We see the output. This is from Jay Alomar. We see the previous outputs. But if we watch it restart again at decoding time step 1, it's very interesting to finally kind of understand this output embedding piece, where previous output is I, and on step 2, we go to AM. AM comes down, flows back through the decoder. It goes to A, flows back through the decoder. And so what we're kind of doing in this encoder-decoder context is we're putting Je suis étudiant into the decoder. And once it comes into the encoder, and once it comes out of the encoder, we're no longer really going back to the encoder. We're simply flowing through the decoder everything we need. All right, so this is what we're doing as we build this thing out. The last piece before training is to build the beast. And so I'll welcome Chris back to, you know, if he has any comments, triple click in on him before he shows us exactly how to build this big bad boy. Off to you, man.
All right. Bear with me. We've got to do some building here. There is a lot of steps. The steps are fairly straightforward, but there is a lot of them. So let's start with our encoder block. Now, our encoder block has a bunch of constituent parts. Obviously, we have our input embeddings, our positional encoding, This is our how information is going to first flow into our model, right? And then, of course, we have our actual block where we're going to calculate or determine some, attention scores and then pass information through our feed-forward network. So we're going to use everything we've learned up to this point to build our encoder blocks. So let's look and see how that's going to happen in the code. First and foremost, you'll notice that we have our self-attention block. This is our multi-head attention. This is going to come from the scale dot product attention that we built above. We have our feed-forward block. That's that feed-forward network we just talked about. That all it is that feed-forward block we created above. And then we have our residual connections. Our residual connections are just going to be a list of these models for blank in range 2, because we need to have those two skip connections, right? Those two residual connections. All we do here is we have the input to our residual connections, which is going to be X. This is the initial input. And then our self-attention block on X, and we're going to connect those. And then we'll do the same thing on the next chunk, but with our feed-forward network instead of the self-attention network. So all this means is as information enters our network, it's going to split off. One chunk is going to go through unaltered, and the other chunk will go through our attention block. They'll connect back again with that residual connection, and then they'll split off again. One chunk will go through the feed-forward network, one chunk will not, and they will be returned together again, and that will be a forward pass of our encoder block. So the basic idea here, right, is that we're going to be able to flow information through this block. And what we want to do now is we want to build a bunch of them together, right? So in this process, with just the one multi-head attention layer, we have 8 different heads. And without trying to oversimplify things too much, the way that I would think about that is we have the ability to understand like 8 different conceptual pieces of information about our input sequence, right? Again, that's an oversimplification, but I think it's useful when we're trying to build intuition. So we have 8 different ways that we're keeping track of these sequences and learning information about the relationships. So what we want to do is we want to have a bunch of them. In fact, we want to have 6 of them. And the way we do this is very straightforward. All we do is we are going to initialize with our layers. Our layers are going to be a list of modules. Spoiler alert, that list of modules will be encoder blocks. Then we're going to have our features. These are actual features that we care about. And those features are going to be what helps us build our normalization. Every feed forward that we do, right, is going to, or every forward pass that we do is going to just loop through that number of layers. And it's going to, take the output of the first block of encoder and then pass it to the next one, and on and on and on and on until it goes through 6 times. And then once that's all done, we are going to do that normalization step. We have some questions. The first part of encoder gives representations or embeddings, or better, just some vectors. After the encoder, we have better vectors. The decoder is clear as it makes. So I mean, the encoder is really good at understanding the information. Basically, we're using it to collect information and have a really a deep understanding of our input sequence, and we can use that representation to better guide our decoder as to what it should be doing. So the idea here is that encoder block helps us build a really powerful understanding of these sequences, and then we can leverage that when we're decoding in order to decode into the best sequence possible. Llama doesn't have this stuff. Llama is a decoder only architecture, so it doesn't use an encoding block or blocks at all. But the basic idea here is, right, we have 6 of these blocks that just feed into each other over and over again, and that's it. You know, that's the whole thing. So we do this process 6 times in a row, and then we wind up with this particular representation at the end, and that's the one that we ultimately wind up caring about. The decoder block, you might not believe it, it's going to be the same thing, but with the decoder stack instead of the encoder stack. So we're going to do the same kind of thing. We're going to have our self-attention block, and then we're going to have our cross-attention block. Then we're going to have our feed-forward block, and then we're going to have these residual connections. Notice that we have 3 residual connections instead of 2. And this cross-attention block is going to reference our encoder's output, right? So the idea is we're going to, in this stage here, this second stage here, right, this multi-head attention block that I'm kind of wrapping my mouse around, this is going to pay attention to what our encoder came up with, right? And this idea lets us have a very rich understanding of what the sequence is. It's going to let us really have a powerful decoding step because we have that information. And that's called our cross attention. We still have, of course, our self attention. And then at the end, we have our feed forward. So same process here. Information is going to flow into this block. It's going to split. One part's going to go self-attention. The other part going to bypass, connect back together for a residual. Then we're going to go through again. We're going to split off our embedding stack information, and this one half of our, or the split that happens is going to go into our multi-head attention mechanism. And then that residual, unmodified, will reconnect on the other side. So we're injecting a ton of information, right, during this cross-attention step. We're really, this is a powerful amount of information we're getting from that encoder stack. And then we'll do the same thing again. We'll split off one last time. One instance is going to go through our feed-forward network, and the other is just going to be unchanged for our residual connection. One thing that I want to clarify in case it's not clear, when I'm saying split off here, they're not like breaking in half. It's literally the 2 of the same thing, right? We don't like modify it or half it or truncate it. It's the same thing. It just goes through 2 different paths, and it is reformed into one at the end. And that's the idea of the decoder block. So that's each decoder block. Now, of course, we're going to have everyone's favorite, and that's going to be a decoder stack. Now, one thing I want you guys to pay attention to is that the forward method only ever takes one encoder output, right? Like we don't have something that's going to change this encoder output between when we first get it and when we complete our loop. So that same information from our encoder stack is going to be injected at each subsequent part of our decoder stack. So the idea here is that we go through that encoder information once to obtain the output, and then we're going to inject that into each block as we move through our stack of 6 decoders. So just to keep that in mind, the idea is we don't want to lose. We want to use that encoded output to kind of ground us along the way. And then, of course, we go through everyone's favorite layer normalization. So that's it. That's the encoder stack and the decoder stack, which is comprised of 6 encoder blocks and 6 decoder blocks. And the code is pretty straightforward, right? I mean, this is straight up a for loop, just looping through each block, using the output to get the next, the next output. And then we just share this information from our encoder stack for each part of our decoder block. That's it. Next, though, we have to have this, linear projection. So we have to have the ability to move this back to tokens or words, right? So right now we just have kind of like, we don't have that at all, right? All we have is this very very incredible representation, but it's kind of useless to us at this stage. So of course, we have to have this linear projection. All this is going to do is it's going to move that back into a space, which is our vocabulary size. So what that means is that we're going to essentially convert this back into a representation where each token in our vocabulary, each possible token in our vocabulary has some, some value associated with it. And this is the idea of how we're going to eventually get back to tokens, right? So we have to take it from this kind of very dense, information-rich representation and move it back into a space where we can deal with it, which is going to be this vocabulary linear projection. Okay, so how do we actually, plug all these pieces together? Well, fairly straightforwardly, we're going to have our encoder block, our decoder block, our input embeddings or source embed, our target embeddings, which is going to be an input embeddings layer. And then we're going to have our positional encoding for our source vector, source sequence, and then the same thing for our target sequence. And then finally, our projection layer, which is our linear projection layer. You'll notice we just instantiate all of these. That's great. We have our encoding stack. Our encoding stack is just going to be, getting the input embeddings, so our source embeddings, getting our source position encoding information, and then passing that information through our newly built encoder block, which is what we saw here. And then we have our decode, same thing. And then we have our project or projection, same thing. Let's look at how we actually stack this dang thing. Okay, so first of all, our input embeddings, we're going to instantiate them with that D model and the input vocabulary size. We have our target vocabulary size for our target embeddings. Great. This is great, right? One half is input, the other half is output. When we look at our transformer diagram, right, we have our input embeddings and our output embeddings. All right, so far so good. Next, we're going to inject that positional information into each of these embeddings. We're going to set up our encoder blocks. Each encoder block is going to be built from exactly what we saw above. And this encoder block is going to have this .append method. Basically, all we're going to do is build a Python list of them. Same for our decoder blocks. And then our encoder stack is going to be instantiated from that list of encoder blocks, same as our decoder stack. Our final transformer is going to be comprised of our encoder stack, our decoder stack, our input embeddings, our target embeddings, our input positions, our target positions, and our linear projection layer. And then we're going to initialize all of the parameters in our model. And those parameters are going to be initialized using the Xavier uniform initialization. And that will return our model. So let's look at this one more time. This transformer class is going to have our encoder block, which is going to be our stack of encoders, right? So our big ol' stack. This is going to be what we care about. The same thing for our decoder, and then the same thing for all of the other layers. And it's going to pass that information through during the encode step and the decode step. And all it's going to do is use that stack to encode and then decode. And then we will get our projection at the end. And that's it. I say that's it. It's a lot of code. It's very dense. But the idea is fairly straightforward, right? All we need to do when we're building our initial transformer is we have to pass in that stack of encoders, stack of decoders. Then when we're actually using that information, we have our encode method. All this is going to do is encode the information. Then we have our decode method, which is going to be used to decode the information. Notice that it takes the encoder output which we already discussed, and then we project that back into a space that's valuable to us when determining what the possible next token in the sequence is. And all of this build transformer is just actually building each layer in a loop and then sending it when we initialize our transformer. And that is, quote unquote, all we need to do in order to have our transformer built. So at the end of the day, just to really high level it again, remember, all the transformer is taking these input embeddings, these target embeddings, right? So say this is like English and this is like Italian, right? Adding positional information to each of those embeddings, so that sequence of embeddings, passing it through many encoder steps where we're going to go through that multi-head attention, feed forward block, encoder block, and then and have the residual connections and the normalization occurring at each of these steps, just like the diagram. Going through the same thing for our decoder into the decoder block. Then it's going to go through the self-attention. Then it's going to go through the cross-attention. Then through the feed forward. Then through that process again 6 times. Remember, each time we're going through a block, we're effectively moving our position a little bit. So we're learning more and more about the sequence. So if we have 6 of these blocks and we have 8 heads in each block, that's going to be 48, right, heads that are learning something about the sequence. And they're each going to learn, we would hope at least, given we have enough input data, they're each going to learn something novel about that sequence. After we're done, we get an output, and all we do is project it back into linear space so that we can use it to see which token is probably going to come next. That's it. That's the whole kit and caboodle. I will pass you back to Greg. Transformer.
Yeah, man. Transformer equals transformer. Encoder stack, decoder stack, input embedding, target embeddings, input position, target position, linear projection layer. That's all there is to it. Well, that was super epic. And now that we've actually built this thing that nobody builds from scratch anymore, we're going to train it. Because what else would we do with it? We're training it, and training is actually what's going to take a very, very, very long time if you really dive in and start doing a lot of this stuff yourself. There's a reason we use pre-trained models a lot. And there's a reason why this is what people are chasing in terms of more and more funding for more and more compute hardware to do more and more training, to reach more and more scale, number of parameters and data trained on. But for today, what we're going to do is we're just going to take a simple example. We're going to be training a BART style model, bidirectional from the left and the right, auto-regressive, using the past to predict the future, previous words to predict the next one. We're going to put all this together, as we talked about, as Chris just mentioned. The encoder is going to feed each of the decoder blocks. And to set this up for training, the paper tells us to focus on a couple of things. Training data and batching, hardware and schedule. They trained on 8 P100 NVIDIA GPUs back when they wrote this thing. And they trained for, they trained a small model and a big model. And they, as you'll see, you can actually train pretty decent models in not a ridiculous amount of time. But obviously the scale and the aims of training have gotten kind of out of control since then. But yeah, for this particular training in the paper, the big models were trained for about 3.5 days. Whereas I believe the GPT models were starting to be trained at the, a month long kind of thing when we really started to see these things working. The optimizer setup, it's an atom optimizer, and they use 3 types of regularization here, including residual dropout and label smoothing. And what we'll have Chris walk us through is the training for a translation task. So he's going to set up the data set, which is a bilingual data set for translation. He's going to build a tokenizer, and he's going to set up the training loop. And the training loop is going to require that we configure the hardware, that we create a directory for saving the model weights based on this configuration. We're going to set up the optimizer, set up the training parameters, those hyperparameters, and then define the loss function. And all of this is going to be very similar to the way that it's outlined in the paper. There's a lot of details that definitely are probably worth checking out if you want to sort of do a more detailed deep dive on exactly how the training was done way back then. Although as you get more into it, you know, you may be more and more focused on GPT only style models. As we've discussed in the chat, the GPT only styles, they came up in the game, and people probably started asking the same question that Iosif asked, which is, hey, what's up with this encoder piece? Do we really need it? And as we studied in our LM engineering class, we saw that, you know, the more and more we trained these GPT style only models, the better and better they got at all sorts of tasks that we thought we really needed to understand the input very well for previously. And, you know, this kind of gave way to the new revolution and the new paradigm in which everybody's racing to build more and more decoder only style models at bigger and bigger scale. And as Andre talked about last week, you know, we don't really see the scaling tapping out. So exciting times we live in. Lots of models left to be trained, bigger and bigger sizes all the time. And today we're going to start by showing you how to train BART style from scratch. And Chris will let us know exactly how long this took and how long you can expect it to take on your own hardware. So with that, Chris, back on stage. Let's keep it rolling, baby.
Oh, yeah. Okay, so who cares about building the model? All we care about is training the model, right? So I'm joking, of course. Building the model is pretty awesome, but training it's even awesomer, so we're going to do that now. In order to do this, we're going to need a data set. Now, data sets are pretty important, as we're all aware. One of the things that is extra important for this kind of training is that we knew first of all, we're going to use this BART style model or encoder-decoder style model to be super precise for a translation task. So we kind of have the idea, right? We have these input sequences and we have target sequences. We can kind of like guess, right? Our input sequences are going to be English and our target sequences are going to be Italian in this case, which is like, you know, the language that we're going to use. Doesn't really matter what you use. The idea is that we have some number of tokens that represents an English phrase, and then we want to reproduce the same meaning, but using Italian tokens or Italian tokens. And this is where that kind of really deep, dense understanding from our embedding model is going to be, or encoding model, sorry, is going to be so important, right? Boiling that English sequence down into some representation that is, you know, rich, full of information, describing what's happening in the sequence, what it means, the semantics, everything like this, right? And then decoding that dense representation into the correct Italian token sequence, right? That's essentially what we're going to do. We're going to encode our English information into some dense representation, and then we're going to decode that into Italian. So we need a very special data set to do this, right? Which is we need it to be tokenized English and Italian. And we need to have a data set where the English phrase means the same thing as an Italian phrase. So, of course, you're going to need people or data with an understanding of Italian in order to create this. The first thing we're going to do is we're going to set our sequence length. Now, our sequence length is something we want to hold consistent throughout the entirety of our training, right? So as we already discussed, when we're injecting this positional information, we have an expectation that our sequence is going to be a certain length, right? And that length is going to be held static, where the model always looks at the full input, even if there's nothing there. So what we're going to do when there's nothing there is we're going to pad our input sequences, right? We're going to just inject a bunch of information that the model will learn means nothing. And then, because we have this fixed size, when we're tokenizing, we need to build to that size every time. And so that's what we're going to do here. We're going to have our data set. We're going to have our tokenizer. This is for our source information, and our target tokenizer, our source and target language. We're going to set up a few special tokens. These tokens are going to be start of sequence token, a end of sequence token, and a padding token. You'll notice that these are specifically using the target tokenizer. So this is the target tokenizer. Every time we go to get an item from our data set, we are going to get, it's stored in a row where one part of the information is going to be our, English sentence, and the other one's going to be our Italian sentence. So we're going to grab the translation column, and then we're going to grab the English language as our source target pair or a source text, and then the target language as our target text. Then we are going to encode our information. It's very tricky because we've used the word encode already, but we're going to get the token representation of our input and output sequences, or our input and target sequences, and we're going to do that using their respective tokenizers. Then we're going to pad everything that we have left except for our input tokens. You'll notice something. We're going to leave 2 hanging off, and then for our decode padding tokens, we're going to leave 1 off, right? This is the idea that we're trying to find what that next token is going to be. So we have to leave 2 off. Then we're going to concatenate for our encoder input our start of sequence token, our encoded input tokens, our end of sequence token, and then our padding tokens. Notice how we need to inject our start of sequence token and our end of sequence token here. This is why we have this -2, right? For our decoded output, we have our start of sequence token, then our input tokens, and then some padding tokens. We do not need the end of sequence token for our outputs because we want to continue to output until it comes up with that end of sequence token. And so that's why we only subtract 1 for our padding tokens. And that's it. We're going to create a label. This label is going to be derived from our input tokens with a end of sequence token, then a number of padding tokens. You'll notice here that we're using these, the same number of padding tokens as we did for our decoder input because we are only injecting 1 token. And our input tokens, you'll notice that they are shifted by 1 from our inputs because we don't have that start of token sequence, right? So our start of sequence token is going to mean that this encoder input sequence is 1 ahead of our label, which is going to become very useful later on. This is it. It's a lot of work, but we need to have these input sequences moved to token representations, and we need to have both our encoder inputs, our decoder inputs, and then labels that we can use to actually train. And that's that. Now we're going to get our actual tokens. So we're going to build our tokenizer. We're just going to use the word level tokenizer here. So we're not going to use subword tokens for this task. We're just going to use word level tokens. Just makes it easier to understand. We're going to have a unknown token for tokens we've never seen before. And then we're going to add these padding start of sequence, end of sequence tokens as special tokens, as well as, of course, our unknown token that we saw above. We're going to pre-tokenize all of our information using the white space tokenizer, which is just going to basically chunk everything into white space. And then the word level tokenizer will actually tokenize the resultant information, right? So the idea here is this pre-tokenization step is going to let us move everything into a consistent format that our tokenizer can expect to be, to be in that consistent format. And that's what lets it see just words, essentially. And there you go. All of this code is basically just loading up the data set. We have our source language or target language. This is coming from some configs that we're going to set up later on. We're going to have our training data set size and our validation size, which is just going to be a split. As per kind of the usual, I would say at least, we have this idea that we do want to do evaluation as we move through our training. And so having the evaluation data set is important. You'll notice that we're just using 90% for training and then 10% for val. Then we're going to actually grab what is the maximum length of our source sequences and the maximum length of our target sequences. We just do this with a loop. You can do it more efficiently if you wanted to. And then we're going to load those data sets using the above information, where we wind up with these, target IDs, decoder IDs, label IDs, and that's it. Basically, you could do this step during training, but it would be less efficient. It wouldn't be as good. We want to pre-tokenize everything so that we can ensure that things are consistent length before we start pushing information through our model. And it just moves that pre-processing step out of the training loop, just to keep things a little bit cleaner. And that's it. Next, we're going to grab our model. We're going to build our transformer. You'll notice that we're passing in our vocab source length and our vocab target length as our max sequence lengths for source and target respectively. We have our max sequence length that we're going to set from our config, and then the dimension of the model is just going to be the dimension of the model. This is just so we can save our weights. Fun to save the weights. There you go. And then this is how we can grab our latest weights, should we have already trained the model. And now we can train this thing. It's confusing looking, but I promise it's not that confusing in reality. So first things first, just need to make sure that we're on the right device. The way that Torch works is it expects everything to be on the same device. It will complain if not. So we have to load things into GPU memory in order to train them with that GPU. So this is the idea is we're going to be loading our models and putting our pre-tokenized information, in a format where it's loaded onto the GPU so that we can use the GPU to train. Create that saving model weights folder we saw the helper function for. Grab all of our data loaders, our tokenizers, and our model, and then move model to the GPU. We're going to initialize our atom optimizer with a learning rate and epsilon. We're going to take those from our config. We're going to set up our initial training parameters, so our epochs and our global steps. And then we're going to use this cross entropy loss function with label smoothing, ignoring pattern as our loss. So we'll see how that goes. First thing, our device, we're going to say CUDA or GPU. You think of it if CUDA is available, MPS if we have MPS, and then as you can see all the way down the line here, if we don't got nothing else, we can do this on the CPU, though it will be a little bit slower. We're going to set our torch device equal to that device. So you'll see here, like the device is going to be CUDA if we have a GPU. And then we're going to set our torch device to CUDA and carry that forward for later. This is just going to make sure that we have that weights folder. We're going to grab our training data loader and our validation data loader. And then we're going to set our model up and then push it to our device. Remember, this device is what we said above here. So we're just shoving things onto the GPU. We're going to use the stock atom optimizer. We're going to use the parameters of our model, since we need to keep track of them in our optimizer. Our learning rate is going to be from our config, and then our epsilon is just going to be a very small number. And again, epsilon is useful. We don't want divide by 0. We're going to set up our initial epochs, our global steps, and then hit up our loss layer. This is going to let us calculate loss, and we are, of course, going to push that loss to our GPU. Everything on GPU. And now we start training. The training loop is fairly straightforward, though it's definitely not the most straightforward thing in the world, but we're going to talk about it and go through each step so that you guys have some understanding of what is actually happening in this training loop. First things first, we're just going to dump whatever cache memory we have on our GPU. This is just to keep the memory size, within limits. We're going to call model.train. Everybody loves model.train. This is going to make sure our model's in a format that's going to allow training to happen, right? So these are going to be trainable. We don't want it to be in evaluation mode, so we don't want it to be in eval mode. And this is because we're not going to evaluate. We actually want to update those parameters. We want to train this model. We're going to use TQDM to show us what epochs we're on. Then, for each batch in our batch iterator, okay, we are going to grab some number of encoder inputs, decoder inputs, their masks, and we're going to shove all those onto the GPU, right? So again, everything needs to be on the same device. So we're going to take this batch of encoder inputs, encoder mask, decoder mask, and we're going to shove that onto the GPU. Now that it's on the GPU, we're going to use our model to encode our encoder input with its mask. That's going to be our encoder output. And this is calling back to that transformer class we set up near to the top of the notebook, right? This .encode is going to pass that information through all of our encoder stack and then return this output. Then we're going to pass the encoder output plus the encoder mask again, as well as our decoder input and our decoder mask into our decode stack. And it's going to flow through all 6 of those blocks and return a output. Then we're going to project that output into our linear space, which is going to be the size of our vocab. That's going to be proj output. So this is great, right? Basically, what we've done is we've taken our encoder input, which is going to be our input sequence, our output sequence for our decoder stack, and we've created some scores, right? So we've created, we've gone through all of the stacks, we've created an embedding. That embedding for each token is going to be then projected into that linear space, and that linear space is going to be associated with our output vocabulary, right? So we've basically looked at all the information, and we've come up with a prediction. Like our decoder output has some prediction, right? We are going to get our label. We're going to send our label to our device. And remember, that label is just that encoder input shifted one to the left. We're going to then calculate the loss using that loss function. And then we're going to print our loss, basically, or store our loss, sorry. And then we're going to update our weights based on that resultant loss. We're going to take an optimizer step, zero our grads out, and then we're going to go to the next step. And we're going to keep doing this on and on and on until we reach our maximum steps. And that's it. So the idea here, right, is that we're going to come up with some output. That output is going to be compared to what it should be. And then we are going to, essentially get a loss based on if it was correct or not. We're going to use that loss to update our weights. That's it. That's the whole process. The training loop is fairly straightforward. The big thing for this particular task is this idea of having your encoder outputs and your decoder outputs. And that's about it. And that's it. And then we train it. And you can see here that we're processing our epochs. This took quite a long time to train. But the idea is we have 910 steps in each of these epochs. And we did 19 or 20 total epochs, finally reaching a loss of 2.447, which is that cross entropy loss based on our predicted token. That's all we did, right? To be fair, it's a lot. I don't want to pretend like it's not a lot. It is a lot. You might also say, hey, Chris, what about softmax, my guy? We're missing softmax. You're correct that we never explicitly defined softmax, but softmax is created as part of our loss layer. So that's going to be when we have our loss layer, which I've lost. Here it is. We are going to have this. This is going to be where softmax exists. So we do not need to softmax our output because that's going to happen as part of this cross entropy loss layer. But just to preempt the question, how about our softmax? How do we actually know which token we're choosing, right? This is going to be handled through the cross entropy loss, so we don't have to worry about it. That's it. Basically, we take our input sequence, we take our output sequence, we send the information first through our encoder stack based on the input sequence, then through our decoder stack based on that target sequence, and then we do what you love to do, which is compare it to what it should be. And the closer we get, the happier we are, and we're just going to back propagate based on that loss. And that's it. That's how you train a transformer. I would not say that it's simple, but the actual training loop is kind of what we're used to, right? We make a prediction, we compare a prediction to the label, and then we update weights based on the loss. And that's what we do. There you go. Training transformers. And I'll pass you guys back to Greg.
Brain. All right. Yeah. All right. That was mega hype, Chris. 2 hours in. It's time to just about wrap it up here, but let's recap, shall we? Chris just trained the brain for us. That was a lot, and we hope you guys enjoyed it. So let's sort of take a look at what we did. Transformer, made up of output embeddings and input embeddings. Positional encoding. The add norm layers. The feed forward networks that were so useful to us to be able to capture new things in new blocks and new attention heads. Those attention heads, we've got the self-attention in the encoder, the masked self-attention in the decoder, and the encoder-decoder attention that passes the information from encoder block to decoder block. So step by step, we tokenize, we embed, we add positional encoding. Within the encoder, we have multi-headed attention, add norm, feed forward, add norm, passed to the decoder, which starts off with masked multi-head attention, add norm, into multi-head attention, another add norm, finally a feed forward network with a final add norm, outputting a linear projection and softmax, allowing us to decide what is the next word. And within the attention mechanism, the tokens and the embeddings feed into QKV, query keys and values. We must assemble these query key value matrices to do our scaled dot product attention calculation. That calculation is done for each word sequence and also done across each head within each multi-headed attention layer. Each multi-headed attention layer, we have to keep in mind, is allowing us to focus on something a little bit different about the world, something a little bit different about the information that we're using for prediction. Kind of like brains in a vat. They all contribute something different. This is that thing that allows us to attend to information from different representation subspaces at different positions. Yes, it is as epic as it sounds. And when we have multiple blocks, multiple encoder blocks, what comes out of the final encoder block goes into each of the decoder blocks. Or, as we talked about before, you might visualize that like this. Translation, I am a student. Each block, each head adds to the cumulative number of total attention heads. And fundamentally, 2 heads are better than 1. 48 heads, probably better than 2. Paying attention to many things is probably a dope thing to do when you're trying to understand everything. Why not an infinite number of heads, you ask? Well, you may have noticed if we did that, training would be even more taxing and even more difficult and even more compute intensive. Balancing data, heads, parameters. This is the art of competing in the market today. So in conclusion, the transformer was the first sequence transduction engine based solely on attention, no convolution, no recurrence, BART style, BERT style, GPT style. You can use any, but GPT style has kind of won out. Generative AI is here, and only decoder blocks are generative. Multi-headed attention is pretty amazing, especially at scale, as we've seen. And so finally, we must say that this is not just ChatGPT. All right. If you're still with us out there, I'd love to welcome Chris back to the stage and answer any questions you guys might have. Chris, what an epic ride, dude. That was a lot, but only 2 hours, 8 minutes, not the 3 we thought it might be. So that's cool. And I learned some stuff along the way.
Pretty fun. Not gonna lie.
Chris, first question, could you please explain the mask? Lily, shout out to Lily for joining us. Nice.
Sure. Yeah. We want to be able to mask some parts of our sequences so we don't know them, so we can predict them, is basically the way you can think of it.
The mask is sort of making it so we don't know what happens next before we try to tell what happens next. That's how I think of it. Is that right?
Yeah.
Yeah.
We need to blank out. So like if we have the full sequence all the time, we're just going to, we'll nail it 100% of the time, right? Because we always have the full sequence. If we're missing bits of the sequence, then we're going to be actually able to wind up training on that objective. So BART usually is trained on what's called a masked language model objective. And this is the idea that we're going to be have components of our input sequence that's masked, and we're able to predict them. That's the big idea of the mask.
Nice. Yeah. Okay. So, Chris, you want to talk a little bit more about feed-forward networks and the way you think about them?
Yeah, sure. I mean, the feed-forward network is basically like, it's just a dense network, right? It's your traditional MLP multi-layer perceptron. The thing we care about it doing is moving our sequence back into an understandable sequence for the rest of our to pass into the next input, basically, and also to help us understand more complex nonlinear relationships that might exist in our data, which are not going to be potentially captured by the attention mechanism by itself. So the idea, again, Harpreet said something that was funny to me, right? That these activations, right? So this is what the MLP can do with these nonlinear activation functions, right? The activations are little boosters nudging you in different directions. And so the way I think about it, though, is that feed-forward network lets us reset our view and look at the sequence in a new way. And so the next heads that look at the sequence are going to see a slightly different version of the sequence, and on and on. And so, we're trying to build this very information-rich, dense understanding of our sequences, and those feed-forward networks are kind of what unlocks the ability to use each of these blocks or mini models in succession without just learning the same thing like 6 times in a row, which would not be necessarily very useful.
So it kind of shuffles the deck a little bit. It kind of, but it's the same deck, something like that.
Yeah, I would say that's fine.
Yeah,
exactly. It just lets us understand our sequences at a deeper level when used in conjunction with those attention heads, so that we're not just teaching our attention heads the same thing over and over again, because they'll just learn the same thing, right? I mean, the actual attention mechanism, the scale dot product attention, it will just learn the same thing if we don't do something to move that sequence around or to move that embedding around. So and we don't care for it to learn the same thing over and over again. We'd much rather it learn interesting things.
And is that an artifact of the way we do positional encoding, or is that more because I guess I'm just thinking about how the sequence moves through fundamentally. So we've got the embedding, and then we add some sort of very interesting positional encoding information, and then we're moving through attention. Normalize, we get to the feed forward, then we're sort of shuffling as we go from encoder to decoder.
And actually between each layer as well.
Right.
So between each encoder stack, and this is the idea, is we can activate those thrusters to get a slightly different,
Activate.
Exactly. Right. And the other thing too is, like, the attention mechanism is not very, we're not going to understand any nonlinear relationships, and we use ReLU in order to capture that information, or an equivalent nonlinear activation function in order to try to capture that potentially non-information or nonlinear relationships that exist in our data, which we couldn't do without the MLP and the nonlinear activation functions. Okay. And yes, what Harpreet said is correct. The activations happens in the MLP, Krishanu. They're not different activation functions. We're going to use, like, for BART, for instance, they used JLU, or I don't know how to say it properly, but the Gaussian equivalent of ReLU. JLU, right? Yeah.
Okay, so Sigong asks, how long did this training take?
Well, it took 20 times 6.5 minutes. So, 120 minutes. 2 hours.
Now, if you weren't on an NVIDIA A100 GPU and you were on, let's say, the free version of Colab, how long do you think this would take estimate?
We'd have to cut the batch size down significantly. So I used a batch size of 16. We'd probably have to cut that in half if we wanted to use a 24 gig card, or even more if we wanted to use a 15 gig or 14 gig card. So like the T4, which I think the T4 is 16 gigs. In which case, I would say it's going to take 8 hours, so 4 times longer.
Okay. And like, if you were to train this and you wanted it to like be awesome, what kind of loss function would you be looking for?
Cross entropy.
I mean, like, I see the loss going down. Would you want to see?
Oh, what the number? Where do we get the number to? Yeah, I mean, sub 1.
Yeah, like low.
We want to see it be as low as possible.
Yeah.
As long as val loss and train loss are harmonious, then we want to see it as low as possible. Like sub 1 is probably. I would begin to be happy.
Cool. Okay, so Fogarty. Is transformer equivalent to the singleton in ML? I'm not sure what this is.
I don't know if he's referring to like a singleton in software. If so, no.
Yeah, maybe if you can give a little more context.
If he's referring to in a different sense, I'm not quite sure, Fogarty, if you want to expand on that a little bit.
Go ahead and expand on that. And then Lily's got a follow-up here. How is the mask created? It says 0s. It says zeros on random tokens.
Yeah, exactly.
Yeah, okay. Is it say 0 on random tokens?
It could be whatever you want. Oftentimes we just randomly omit some sequence. It depends on what objective we're trying to use as well. We might only mask the end of the sequence. But the idea is, depending on your objective, we're going to append that mask at various parts of our sequences.
Nice. All right. Well, looks like we made it. Yeah. Well, thank you, Wiz, for walking us through all of that. I certainly learned a lot. I'm ready to get back after and give this another shot soon. Another iteration, another day, pushing the understanding of the transformer forward for myself and for hopefully some others as well. It's a training model with only one layer. Fogarty.
It definitely has many layers.
Okay.
So the transformer architecture itself has many different layers. So obviously we have each of the embedding layers. We have the all the layers required to do our linear collections. So many layers in the.
Yeah, maybe we're just talking about a single layer neural net. Is that what we're talking about, Fogarty? Something that actually captures relations between.
We can definitely condense it into one block.
Okay.
Right. So it can be turned into a module. That's what we're oftentimes going to do. So in that case, yes, it can be condensed into a module. So our encoder block is a module. Our decoder block is a module. And we can just chain those together for as long as we like. Like, for instance, Llama 2 is like Bloom is 32 of those layers in a row, the decoder layers, right? But each of them is a single module.
Yeah, it's easier to think about in the decoder only style, right? Yeah. Okay. Yeah. All right. Now it's making sense. All right. Got it, Fogarty. Yeah. So, I mean, you can stack on stack and stack and stack, but, it just gets to a compute situation where you're like, yeah, you don't want to be part of that anymore. There's got to be a better way. And in fact, I think that's what people are focused on figuring out. So awesome. Thank you, everybody, so much for joining us. Thank you, Lily, Seagong, Fogarty. Thank you, Harpreet, shouting out, crushing in the chat all day. Krishanu, thanks for everybody engaging and sticking with us all the way through. We look forward to bringing you more content soon. And Chris will go ahead and wrap it up here. Thank you, man. Thanks everyone for your participation. This has been brought to you by AI Makerspace. This is a special long form event. We hope to do more stuff like this in the future and figure stuff out live with you guys. If this resonated with you, you may be interested in checking out our LLM engineering course that the next cohort does start in January. It's a deep dive on everything from LLM model architecture and training. Essentially, it picks up right where this leaves off, and you'll learn how to do everything from unsupervised pre-training to supervised fine-tuning, how to deal with prompt engineering and instructions and RLHF and the whole bag. So you can train your own stuff from scratch. If you'd like to see more stuff, we're also going to go ahead and share a feedback form with you in the chat. But that's it for today. If you'd like to join an upcoming event, check out the AIM community calendar and the AIM community Discord. I'll drop those in a comment on the YouTube video for those of you watching outside of the context of today. So thank you so much. Thank you, Chris. Thank you, everybody. And we hope to see you again real soon. Until then, keep building, shipping, and sharing, and we will certainly do the same. Bye, y'all.